So cool. Okay. Let's talk about WebAssembly. Very quick introduction who I am. I work at Anaconda. In the Python community, I've been known for many projects in the past. Like I was involved with PyPy, HPy, PDB++, other things. Since 1 year ago, I work at Anaconda on the PyScript team, which is why I got interested in WebAssembly and in this technology, which is incredibly exciting. And I want to, well, talk to you about this. So WebAssembly, what it is. As I said, it's exciting technology. The naming is a bit weird because from my point of view, it's not strictly web and it's not an assembly. In the sense that it's not assembly language. So what is it? I did what everybody is doing these days. I asked the ChatGPT. And it told me that WebAssembly is a binary instruction format for a stack-based virtual machine. What does it mean? So, like, it's what ChatGPT said. It's a virtual machine in the sense that you can think of it as a CPU. It's a virtual CPU. It's an instruction set, binary format, that can execute low-level code in a fast way. An incredibly good property of WebAssembly is that it's designed to be sandboxed and safe, which means that you can run untrusted code in your browser, for example, and be sure that this untrusted code cannot harm you. I say the browser, but it's not the only way of running WebAssembly. That's why I stroke out the web part in the first slide. It's a virtual CPU, it's a virtual machine, you need an emulator for it. And all the browsers, all the modern browsers support WebAssembly natively, but it's not the only way. Node.js also has a virtual machine, a WASM virtual machine inside. There are other runtimes which are independently and then can run WebAssembly code. So for example, OneTime, WASMer, and etc. And since it works in the browser, like it's really the most ubiquitous VM ever implemented. Like it can literally run on millions of devices right now. It's a web standard developed by Bytecode Alliance, and it's also why it's getting a lot of traction. It's important, and part of the reason why it's so successful is that you can use WASM as a compilation target. So you can take C code, C++, or other languages, compile it to WebAssembly, and run it at a very, very fast speed. It's nearly native speed, which means that you can take legacy application and run them, for example, in the browser in a very easy way, something which was not possible before. Example of applications which were ported to WebAssembly and compiled to WebAssembly are like Photoshop or AutoCAD or CPython, as we will see later. It's like similar to what JVM and .NET promised years ago, but the key difference is really that it's low level. So you can take C and compile to WebAssembly, something that you could not do with the JVM. Like maybe you can compile C to JVM, but using some hacks which are slow. So WebAssembly was really designed with this in mind, and not only, but this in mind. From my point of view, the best naming for this should be low-level virtual machine, apart that it was already taken, so they cannot use it. So yeah. Naming is hard, we know. Like we always say this in the PyScript team. Hello world in WebAssembly. This is the simplest thing that I could do. So I decided to use C as a compilation language for the WebAssembly because I hope that many of you know it. Factorial function, computing, well, the factorial in C, very easy. We can compile it to WebAssembly using Clang, so part of the LLVM suite, but this is the compilation line that don't care about this. What happens is that like you start with factorial.c and you get as an output factorial.wasm. And which is a binary. But if you want to inspect it, to see how things work at a low level, you can use a tool which disassembles it and emits like a readable way of, well, a readable format of WebAssembly binary. This format is called WAT. And the reason why I want to do this was just to be able to use this meme. WebAssembly text format. This is the output of WASM to WAT of the on the WASM file which I compiled before. I'm not going to speak too much about this. Like This is really how it looks like, and what you can see is that a WebAssembly module contains a lot of functions in this Lisp-like format, and one of these is like factorial, which takes, this is the signature, so it takes a parameter which is an integer 32-bit, it returns an I32, and we have local variables, and they are compiled to CPU registers. And that's why it's fast, because this language, this instruction set is low-level enough that it can be matched very, very well on a real CPU. This is the loop which computes the factorial, and like I32.add is the instruction which adds to local variables which are of this type, and it's really can be compiled into a single x86 instruction or things like this. This is how the virtual machines implement running WebAssembly. And since it's like we can run WebAssembly in the browser, let's try a live demo. We will see whether it works. This is the code which you need to load a WebAssembly binary in the browser and run it from JavaScript. I'm not going to explain the details, but like the important thing is that here we are fetching the binary code which was compiled with which was compiled by CLang before, and then we instantiate the WebAssembly module, and then we get something which we can call from JavaScript. And here, if I click on compute, my JavaScript code invokes this function and writes the result here. So this is like the basic example of taking C code, compiled WebAssembly, running it from the browser using JavaScript. But WebAssembly is like, it can run on multiple runtimes, not only in the browser. So this is another example in which you can use the same binary code as before and run it from Python using WASM time, which is one of the many virtual machines available. And it's basically the equivalent of the slide before. I'm not going into the details, but you can see that we are instantiating, reading the binary, getting a function that you can call from Python. And I want to be very clear, this is not Python in the browser. It is CPython running on my real CPU, running a WebAssembly module which I compiled. It has nothing to do with what we do in PyScript. We will see later how we turn things upside down. Okay, so basic example done. What you can do with WASM and why everybody is so excited about it. So something that you can do is to computation. Like you can compute a lot of things, burn your CPU, make the planet even hotter, and yes, and that's it. Yes, like by default, you cannot do anything else with WebAssembly, which you don't have access to the file system. You don't have access to the network. You cannot do any I/O. You cannot do any system call. You don't even have libc. So like, it's the reason why it's safe, you can see. But it made me think, okay, what's going on? Because how can we turn tears into something useful? And the key part of the technology is imports. So when I declare a WebAssembly binary, a function in WebAssembly, I can declare that it imports some function, and it can call them. And the imports are provided by the host. In the example before, this example here, the host is JavaScript calling WebAssembly. In this example, the host is Python calling WebAssembly. And the imported functions are provided by the host, which means that the host has full control over it, and it can implement them as it wants. Another example in which we see how this import actually works is what usually it's the hello world. Like you print something from your program, but hello world, the normal hello world doesn't really work in WebAssembly because by default you cannot print anything. So to print, you need to define some external function, print str and print int in this case, and we can call them from C. And then when we instantiate the module, we need to provide a way to implement this functionality. And if I compile it, disassemble, I get this WAT file, and you can see that inside the WebAssembly module, now the WebAssembly module specifies that in order to work, you need to provide these two functions from the environment. And then if I try to run it, I'm not going to demo it in the browser now, but like you can have the demo which works from Node, for example. So the code is very similar to the one before. I get the WebAssembly binary, I instantiate it, but the key part is that I'm providing this import the environment containing imported function in which I have print int and print str, and then I can implement it in JavaScript, in this case, to do what I want. So print int, well, it takes an integer and, well, console.log it. Print str is much harder, and we will see now how it works. And when I instantiate it, I pass the import object to the WebAssembly runtime so that it knows how to, well, fill the gaps. And how do I implement printing a string? In WebAssembly, memory is just a giant WebAssembly array. And the WebAssembly code inside the module think it's RAM, and it has pointers, and like the C code manipulate the pointer as we are used to, but actually they are offsets inside this array. And from JavaScript, I can access this array and see the content of the RAM of the module. So my function print str takes a pointer, so which is like an offset, and with this magic, I don't know JavaScript, I just copy and pasted things around. And I can access the bytes in the memory using something like this. And then I have something which is very inefficient, and don't do it at home, please. Don't tell people that I showed it to you. But there is a way of getting the individual bytes from the memory, and until I find the last character, which is a 0, and which is the end of the string in C. So I fish all of them, combine them into a string, and then finally I log the string. I don't have the demo in the browser. I have it here. Let's see if it works. So I can node run counter node.js, and it works. Well, nothing spectacular, of course. And I can do the same in Python, like using the same WASM time module that I showed before. And in this case, well, it's very similar again. I can get the memory. In this case, memory is like an instance of some class provided by the WASM time interpreter, and I can read the memory. This val is a number, so it's a key value of my strings, and then I can combine them into a string, and then finally print it. So this is like, it's like I have 30 minutes, so I cannot go into many details, but like this should give an overview of how you can start from nothing, like WebAssembly with no external access to anything, and slowly build your way up to provide functionality. One example is files. By default, I cannot access the file system from WebAssembly, but I can write imported functions which provide a functionality for opening a file, reading a file, writing to the file system, and etc. And what they do is really up to the host. Like me instantiating the WebAssembly module, I decide what opening a file means, what writing to the file means, where these bytes go to. And if I'm the host, I can decide that I can forward them to the real file system so that my WebAssembly code can read my files, or I can implement a completely virtual emulated file system, which is what happens in the browser, for example, for Pyodide and PyScript. So in Pyodide, you have a virtual file system which contains a standard library of Python, and you can import them, and then CPython fopen the file, and then after many layers, you arrive to the imported function, which is written in JavaScript, and reads the file, which is like somewhere in memory in the virtual file system. So I don't want to do all of this manually every time I want to use WebAssembly. And I need a way of having normal functionality, which I expect for legacy application, importing files, printing to the console, I/O, networking, etc. And there are basically two big ways of doing it. The first is emscripten, which is historically the first tool chain which was built around WebAssembly. I think that emscripten actually, well, was created before WebAssembly. you can think of like a runtime environment which fills the gap between WASM and POSIX. So it implements a complete POSIX system in a way that can be exposed to WebAssembly. So if you have your C program, compile it using the emscripten toolchain, you have something which works in the browser almost out of the box with the asterisk. And it contains a lot of functionality, existing libraries available. But since the runtime of emscripten is implemented in JavaScript, it can work only in a context in which you have a JavaScript interpreter which can run this runtime. So it works in the browser, it works in Node, but for example, it doesn't work in the other runtimes, like WASM, which I showed before. And the other alternative is WASI, which is basically a standard library of imports. Like it's a standard which defines a lot of functionalities to open files, to do networks, and a host, like a runtime, can decide to support WASI, and then it means that if I have a binary which was compiled against WASI, then I can run it on top of any runtime which exposes the WASI functionalities. And it basically feels, it's more or less the same kind of, it solves the same problem as emscripten, but with a different mindset. Usually, it's not completely true, but usually emscripten is used when you want to target the browser, and WASI is used when you want to run your code on the server, like on a real system, because WASI often is like forwards the call to the real file system. But for example, you can also polyfill WASI in the browser and run it also in the browser. Like it's not completely separate, but it's a good approximation. A good way of thinking about it is that WebAssembly, WASM, is the CPU, and WASI or emscripten are the operating system on top of it. Not completely true, but it's a good approximation. WASI contains a lot of different functionalities, so you can decide which functionality to expose, how you can decide to expose only the file system and not the network, or things like this. WebAssembly is not only this. There are a lot of exciting features which will come in the next weeks, months, or years, I don't know. WebAssembly was designed as a MVP, minimal viable product. So they decided to do the minimal thing that could be useful, and so that they could standardize, implement it everywhere, see whether it was useful. It was. And now on top of it, they are adding new functionalities, and they need to standardize them, and so there is a lot of process involved. But WebAssembly is getting higher and higher level, so that if the current situation is that WebAssembly is very good for C and C++ code, the newer functionalities will make it a better compilation target for higher level languages. So for example, you can have native exception in WebAssembly, support for garbage collectors, other things. Exception handling is a good example, because it means that if you have exception handling at the level of WebAssembly, and I have two languages which implements their respective exception in terms of TILs, functionality of the virtual machine, I can imagine raising an exception from C++ and catch it in Python, or in Rust, or in whatever other language supports exceptions. And like, if you expose, it doesn't exist yet, but if you expose classes as a WebAssembly feature, then you can have classes implemented in one language and consumed by another. So it's an exciting technology for multi-language interoperation. We are not there yet, but I think that this is the direction in which it's going. I know that not everybody agrees with me, but we will see how it goes. How does all of this relates to Python? One way of using WebAssembly in a Python context is what I showed before. So I have Python running in my CPU normally, and I can run WebAssembly code from it. And this is useful, for example, if you want to implement a plugin system, because I can run untrusted code and plug in into my application without worrying that it can break things. The other way is do the opposite, which is not run WebAssembly from Python, but take Python and compile it to WebAssembly. So you can take CPython, which is written in C, and compile it to WebAssembly, and then run the virtual machine of Python inside the virtual machine of WebAssembly. And this is what we do, what we think about when we talk about Python in the browser. So there is Pyodide, which is the project that PyScript builds upon, which does exactly this. So you get a WASM binary, which is the Python interpreter, and then you can feed your Python application to it, and it will execute it as it does on x86 or ARM. You can compile CPython vanilla on WASM, and like it's tier-free support, which means that well, the core developers try to not to break it without any promise. That we are thinking and trying to make it tier 2, which is more official support, let's say, and they will promise and try not to break in the next releases. And then you have Pyodide, which takes this core functionality and on top of it adds a lot of other things, including external packages, NumPy, SciPy, Matplotlib, and etc. And then on top of Pyodide, you have PyScript, which makes everything very easy to use, basically. You can also have MicroPython, which is another implementation of Python, which is like... okay, yes, I'm not going to explain the joke, but which is very, very small and fast, so it has its use cases in the browser. You can use Jupyter Lite, which is like Jupyter, but using WebAssembly and Pyodide so that it doesn't require a server. And you have PyScript.com, which is the new service that we're launching at Anaconda to make very, very easy to write and host and deploy PyScript application in the browser. And by the way, you can see that these slides are hosted on PyScript.com, and like, I'm a low-level guy. I know about garbage collectors and JIT compilers. I don't know anything about the web. Like, if I was able to deploy this, like, it should be easy, and also for beginners, hopefully. There are more talks about PyScript at the conference. 2 of them were in the past, but fortunately we have videos, so you can look at them. And I just few hours ago I was listening to this PyScript for Education, and it was very, very nice. And the speaker was very excited about WebAssembly. He really explained how it's useful. It was very nice from my point of view to see how it's used in the field. And I was listening to the talk and say, wow, it's PyScript is very cool. I would like to help them. And then realize that I'm already doing. And just after lunch, there is Fabio's talk about PyScript, what happened in the last year, what are the upcoming features. So I suggest, if you're interested in the subject, to to come to the talk and listen to it. And by the way, Fabio just showed me how it wants to run the talk. It's full of live demos, and it will try to run things in the browser lively. And I told him that it will never work. I'm sure something will break. So if you want to see how it goes, you should really try and, yes. 1:30 in room 355, okay, upstairs. And then there is the Anaconda booth in the big room, and you can ask us about PyScript. There are demos. You can get some swag. You also have we also have Rabbit PyScript hoodies with the Rabbit, and it's not we have few of them available, so it's not for everyone. A good way of getting the hoodie is present a PyScript talk at PyCon, because Blake asked for one, and I think he will get. So next time, if you want the hoodie, you can present a PyScript talk. And on Sunday, we are going to have an open space, and then we are there also for the sprint. I think that I'm done, so I see I still have 5 minutes for some question. These are the links for the GitHub repo, which contains the slides, so you can also get the source code. This is the pyscript.com URL, which contains the slides, and honestly, it's not very nice URL, and I think that we are getting nice URLs soon, they promised me. And I also, well, this is the shortened way of it is the same, but yeah. And that's all. So if you have questions, I will be happy to answer.
If you have questions, please come forward to the mic.
Thank you for the talk. It would be super cool if it would be possible to compile actual Python code, not CPython, but Python code into WebAssembly. Are you aware of any work in this field?
Not really. Compiling Python to WebAssembly is not easier or harder than compiling Python to C. And Python is not really designed to be compiled. So it's the kind of, it's the same kind of problem. I think there is MyPyC, which compiles Python annotated with typing and emits something, but I don't know how it really works and whether it works well or not. I think that if we want Python to be compiled to WebAssembly, we need to tweak the language and remove some of the dynamicity and have, like, JavaScript Word does the same with AssemblyScript. So you have JavaScript, which is like very dynamic, similar to Python, and AssemblyScript, which is basically a different language with a syntax which is similar to JavaScript, but is designed to be easily and natively compiled to WebAssembly. So this is a way of doing it for Python, but nothing like this exists as far as I know.
So my follow-up question is related to more with the compatibility of PyScript with the different types of JavaScript engines, whether it's SpiderMonkey or QuickJS. So is there going to be more future support for some of the non-native JavaScript compiler, JavaScript runtimes, such as we usually have most popular one is like V8, right?
Yes.
So if we have compatibility with SpiderMonkey or with QuickJS.
I don't know the answer, but I don't know the precise answer. What happens is that Pyodide, for example, runs on every runtime which supports WebAssembly with all the functionality that it needs, and I don't know exactly what they are. If SpiderMonkey supports them, yes, it just works. And I mean, PyScript works on Firefox, so I guess that SpiderMonkey should just work, but I'd never tried. And QuickJS, I don't think that it supports WebAssembly, so this is no. But maybe it does. I don't really know.
Thank you for the wonderful talk. You learned a great deal. I had a low-level technical question. So you showed us the WAT file, right? And it had instructions which was WebAssembly specific. How thin is the translation layer between that and actual assembly or actual machine on the CPU?
I don't know. I never look at the disassembly code on the CPU. WebAssembly is really designed to be a good target for this, and then it's really up to the runtime. I think they have a JIT compiler which generates the code. You can expect a bit of overhead, I think, on the order of 20%, 40% compared to like native code, but I think that it's getting to improve because, for example, they are adding support for SIMD instructions. So like you can. Currently, GCC compiling to x86 can use automatic vectorization, and compiling to WebAssembly it cannot. But when they will have these new low-level instructions, we'll be able. So in theory, we should catch up.
Thank you.
Hi, yeah, great talk. I also learned a lot. But I'm curious what you think about the sort of conflict between sort of the first half and the second half of your talk that I saw, which is that the promise of the universal binary or something like that, I forget exactly how you phrased it, or the universal virtual machine, seems at conflict with the difference between WASI and WebAssembly, or emscripten, and all these features you also mentioned that are going to be added. Do you see this as sort of in conflict, or is there a way to make sure these things all, present one easy experience to the poor developer who has to produce WASM code?
I don't see it as a conflict. I see it as different platforms which are used for different things. And I mean, emscripten is a way of running things in the browser which works very well, and it gives you some strengths. The fact that it works on emscripten doesn't mean that you can. So okay, wait. The difference between emscripten and WASI is when you compile things. So if you have something which is compiled to emscripten, it works only in an environment which supports JS. But from the source code, you can compile it to WebAssembly, to WASI, and to emscripten, and then deploy it on different machines. But really, it's really up to the runtime. For example, I think that there are Cloudflare workers which consume WebAssembly binaries, and then it's up to Cloudflare to decide what they want to offer. And they might not offer all the WASI functionality. So there is always be this kind of tension in the sense that every runtime decides what to offer. And it's not that WASI solves everything, because maybe runtime offer only a subset of WASI, and then you need to ensure that you use only this. But I think it's not solvable from this point of view.
Awesome. Thanks for clearing that
You're
up.
welcome.
Thank you, Antonio. That was super
Thank you.
informative.